Let's look at a single cache that is 16 kilobytes in size. Let's look also at a single cache that is 128 kilobytes in size. Let's look at no cache, simply we will just access the main memory. And let's look at a hierarchy that has this kind of cache as the first level cache and this kind of cache as the second level cache. We will look at the hit time for these, the hit rate for all of these, and the overall AMAT. So a 16 kilobyte cache might have a hit time of 2 cycles, a hit rate of 90%, so it gives us an overall AMAT of 2 plus 10% of the time we have the memory latency. Let's say the memory latency is 100 cycles. In that case, we end up with an overall AMAT of 12, 2 from the hit time and 10 on average from the miss penalties. Now let's look at a larger cache. This cache might have a hit time of 10 cycles, but a hit rate of maybe 97.5%. This is a bit high for such a cache, but let's say it is. The AMAT, when this is used alone, would be 10 plus the miss rate times the miss penalty, and we end up with 12.5, which is a little bit worse than with a smaller cache. So having a larger cache alone increases the hit time, improves the hit rate, so it may or may not improve the AMAT, but either way the AMAT is not going to improve a lot. Of course, having a cache is still lots better than not having a cache. Not having a cache means that our memory has a hit time of 100 cycles, basically the memory latency. It hits 100% of the time, so our AMAT ends up being 100 plus 0 times the penalty, because it never misses, but we still end up with 100 cycles per access, which is way too big. So obviously having a cache is better than not having it. So now let's look at the cache hierarchy. The hit time is different depending on which of the levels we hit in. The hit time is still going to be 2 cycles for a level 1 hit. For a level 2 hit, however, we first check in level 1, so we pay 2 cycles to check. Then we access L2 and have a hit. So overall now it's going to be 12 cycles for a level 2 hit. The hit rate is going to be 90% for L1. It's still the same cache as if it was alone. And of all the accesses that go from level 1 to level 2, we will have some hits. Because the L2 cache has this hit rate when working alone, of all the processor accesses, it would have a hit on this many. But of all the processor accesses, those that hit in L1 probably would also have been hits in L2. So this cache really has a 75% hit rate of all the things that go into it. It would have this hit rate if it was alone, but the L1 cache is filtering all of the easy to hit accesses, so the L2 only gets 75%. Basically, it only gets to see kind of the worst 10% of the accesses, and for those, it's only having a 3/4 hit rate. But the AMAT is now going to be 2 for L1 hits, plus 10% of the time we have an L1 miss. When we do, we have 10 cycles to access L2, plus 25% of those also end up accessing memory. So when we compute what this is, it's 10 plus 25. So the overall miss penalty for a level 1 miss is just 35 cycles. It's much better than what it used to be when the L1 was working alone. And we finally end up with 2 plus 3.5, which gives us an overall AMAT of 5.5 cycles. This is much better than either of the 2 caches working alone. And it's much better because really we're having most of the accesses hit using the hit latency of the fast cache. Some accesses have a higher hit latency in the second cache, and fewer of them pay this huge memory latency. So this is why cache hierarchies work better than individual caches and why we have them. It is not enough to simply have a large cache if it's also slow. In that case, you can combine their good properties so that most of the time we get this hit time. But overall, as far as the memory access is concerned, we really have this hit rate in the combined cache.